Hello, welcome to calculus class. Today I would like to discuss 5 wonderful special limits. I will discuss special limit number 1. You all know it, and the reason of my presentation is I came across through the YouTube postings, and you all talk about the squeeze theorem, which is a nice, correct way, but this is undergraduate level of approach to prove this wonderful limit. I'll discuss it, and in addition to that, I will look at the mathematical analysis approach, how we prove it in mathematical analysis. When solving limits, you know there are 7 indeterminate forms. 0 over 0, infinity, infinity, 0 by infinity, infinity minus infinity. It's important they have the same sign, both infinities the same sign. 1 to the power of infinity, 0 power of 0, infinity power of 0. Those first 4, there are many ways to resolve that. Actually, dividing by 0 is a problem. We can't divide by 0. It's just a big problem. It forks out many conditions when we divide by 0. The result may be blown up with plus or minus infinity if you divide the constant by 0, or 0 over 0. We do not know right away. Could be positive, could be negative constant, could be 0, could be plus infinity, could be minus infinity. So we are now smart enough to resolve this situation. And there are common ways to resolve it. Whenever this division, factoring our, let's say if it's a rational function, factoring polynomials. Factoring helps us to reduce fractions. While reducing fractions, we can get rid of those ambiguities, those indeterminate forms, and everything may be determined in that case. Reducing fractions, L'Hopital's rule helps us to get rid of those indeterminate forms. You know how to apply it. You may apply it a couple of times, many times. Some special trig functions, they lead us to factorizations. Again, the factorizations help us to get rid of the ambiguities. Multiplying by the conjugate factors helps us to clear up the radical signs, some irrationality, which is also useful. This is how we actually resolve our indeterminate forms. Last 3, second special limit, we'll discuss it later, helps us to resolve the last 3 indeterminate forms, and also we look at the logarithm of the function, which helps us to get rid of the exponential form. It may lead us to one of those. Once you take the log, analyze the log of the function, look at the limit, may lead us to one of those first 4 indeterminate forms, and we will be able to resolve it. So the first wonderful special limit, you all know it. We go back to old times, to ancient Greece. First known limit, when x goes to 0, of sine x over x, it's equal to 1. If we look at this function, sine x over x, looks like this kind of relaxing oscillation. The relaxation of oscillations, it's an even function. Odd over odd functions, even function. And if you look at any points here, there will be no problem. Sine x over x, non-zero value by non-zero value, you'll be able to calculate. The problem is here. The problem is at the origin, sine 0 over 0. Sine 0 is 0 over 0, we have 0 over 0 indeterminate form. And actually, it's easy to resolve it. It's exactly one constant, positive constant in this case. And there are many ways to prove it. One of the ways is the squeeze theorem. You look at the unit circle, your angle is x. It's important if you look at the first quadrant, x from 0 to pi over 2. So in this case, I can set up the relationship between the 3 shapes, the 3 areas. In the first quadrant, the triangle, consider triangle AOB. The sector AOB, the sector, it's a part of the disk with the vertex at the origin, centered at the center of the circle, and the sides equal to radii. It's part of that disk, kind of part of the pie, the cake. And the triangle AOC, the large triangle AOC, and obviously easy to visualize that. This is the relationship. Smaller triangle, the segment, and the larger triangle. This is how they related in this case. Going back to the trigonometry, geometry, the area of the smaller triangle have the sum base by the height. One half the bases are the radius. The height is the hypotenuse by the sine. The hypotenuse is second radius. So the product 1/2 r squared sine x. It's the area of AOB triangle. The area of the segment is half the product of the radii multiplied by the angle between them in radians. X is in the radians. 1/2 r squared x, and less than 1/2 r squared tangent x. It's a line of tangents here. The larger triangle AOC, the area is equal to 1/2 the base r by the AC, which is equal to OA multiplied by the tangent x will give me AC. So that's the area of the larger triangle, and again, it's the relationship between them. And the setup comes from this condition. Now, simple algebraic manipulations, multiplying all the sides of this compound inequality by 2/r squared, which is a positive value. All the signs are preserved in this case, so we just clear out fractions. Sine x less than x less than tangent x. And we all know that relationship, it always works for the values of x in the first quadrant. This condition. This is what it works. And again, continue simplifying it, multiply all the sides by another positive value by 1/sine x, or dividing by sine x everything. Sine x is positive in this case. All the signs are preserved again. So with 1 less than x/sine x, tangent over sine x, it will be just 1/cosine. Now, flipping all the reciprocals, all the positive values, flipping reciprocals, I have to reverse the signs, and this is what I have. Flip 1 over cosine. Now cosine will be the smallest, sine x over x in the middle, and 1 will be the largest value in this case. And this is wonderful result. You all say this is what we have for the setup. When we look at the limits now of cosine x, when x goes to 0, it's no problem. Cosine 0 is 1, so the smaller value tends to 1. The larger value, constant of 1 is 1 when x goes to 0. The larger value goes to 1, and the value in the middle force to approach to 1. It's called the squeeze theorem. Sometimes it's called the pinch theorem. Sometimes it's called the sandwich theorem. In some countries, they even call it the theorem about two policemen. So this is the lawbreaker. In the middle, two policemen got him, and he cannot escape anywhere once they got him. Two policemen. So that was a nice, beautiful way. It's kind of undergraduate level. Why? Because you based your proof upon the squeeze theorem. But how do you prove the squeeze theorem? This one we look at the analysis part of it. The analysis part, more detailed. It was developed by Cauchy. When you're given a function, f of x, which has a limit, has a limit L. Limit L when x approaches to A. So we have all those conditions. X approaches to A, function has a limit L, then the detailed part of function having a limit says, we discussed that in analysis. It was developed initially by Cauchy, and the statement was modified by many people. They contributed to the statement later on. For any arbitrary small positive epsilon, there exists delta, and actually delta is a function of epsilon. This is what's important. I need to find that's important to find this function delta depends on epsilon, which is also positive because I'm using it for the neighborhood of my x variable such that, so delta positive is such that when for any x minus a less than delta, what does it mean? It means that my x is in the delta neighborhood of a. X approaches to a, absolute value less than delta in the neighborhood. So it's called, it's the delta neighborhood of a. The delta neighborhood of a, of my x, it implies, exactly implies that the absolute f of x minus L less than epsilon. What is that? That's the epsilon neighborhood of f of x. So my f of x is in the epsilon neighborhood of L. So what's important here? There are 4 clauses, and to prove that my f of x function has element L, I need to find, first of all, the delta function depending on epsilon and relationship between those relationships. Yeah, this relationship between those 2 clauses actually helps me to find my delta. So in our case, f of x is equal to sine x over x. L is equal to 1. We're trying to prove that it's equal to 1. A is equal to 0. Yeah? That's the constant where my x is tending to. It's going to 0. So we have, in our case, we have for any epsilon more than 0, there exists delta depending on epsilon positive, also positive, such that for any x, the delta neighborhood of x, which is the absolute value x minus 0 less than delta. A is 0. So x minus 0 is just x. So with the absolute value of x, so the absolute value of x less than delta. When the absolute value of x is less than delta, it exactly implies that sine x over x minus 1 is less than epsilon. This is what I need to prove. This is my situation here. Yeah, that's the analysis part. We look at all the details. Like I said, the analysis comes from Greek analysis. It means that you have a big problem, you break it down to smaller sub-problems, sometimes elementary sub-problems, which means break it down all the way so I cannot break them down anymore, and you research each sub-problem separately. This is what we exactly look at. It has very nice visual interpretation. So I need to modify my statement to find the relationships I have. So this is where I stop at this one, and please remember we set up all those conditions, relationship, when our x is in the first quadrant. Yeah. So which means if I subtract 1 from all the sides, I'll be sine x over x minus 1. So the cosine x minus 1, I need to look at that, yeah? Will be less than sine x over x minus 1, and it's less than 0. And again, I have this relationship, all the negative values here. This cosine is less than 1, minus 1, negative. Sine x over x is less than 1, minus 1, negative. This is the setup of the negatives. So I can multiply everything by minus 1 to flip them to the positive part, flipping the signs, which is 0 will be on the left. Oh, minus 1 by this will be 1 minus sine x over x, and less than 1 minus cosine x. Yeah. This is what I need to look at, because 1 minus cosine x is actually some special trig formula. We remember it, we all know it. It helps us to make some simplifications. You all remember 1 minus cosine x is the power reduction formula, 2 sine squared x over 2. That's this one. So when you want to reduce power, you double your argument and vice versa. Yeah? From power 1 to power 2 to power 1, but the argument is doubled from x over 2 to just x, which is doubled, and vice versa. So our reduced relation, so it's equal to 2 sine squared x over 2. And actually it's less than just 2 sine x over 2. Yeah, no square of the sine gets larger because sine is between 0 and 1. And also in this first quadrant, remember this setup, sine x over 2 is less than x over 2. So it's less than 2 by x over 2. So now we have wonderful result. We almost there at our end of the proof. This is what I have here. If I look at in general for all the x values, the absolute values, I can write this. 0 less than absolute sine x over x minus 1 absolute value. It turns out that it's less than, look at this, less than the final result, the absolute value of x. Look at this. I just connected those two clauses. I just connected those two clauses by using some trig special formulas. Again, some trig special formulas sometimes help us to resolve ambiguities, indeterminate cases. What does this mean? This is my delta neighborhood of x around 0. Yeah, by the setup, it's less than delta. Yeah, and we want this condition, absolute x less than delta. We want this condition to generate, imply that my sine x over x minus 1 absolute value to be less than epsilon. Will it generate? Yes, it generates. In which case, when I choose my delta, say equal to epsilon in many cases, yeah? So actually, this is what I can take. I can choose my delta function equal to epsilon. And there will be some special cases, because my epsilon is arbitrary positive number. So when or if my epsilon could be actually more than pi over 2. Yeah. So if epsilon is more than pi over 2, so if there's a more than pi over 2, then my x, if epsilon is equal to delta, x could be outside of this condition. X could be more than pi over 2 here. And this setup was based on that condition. So I cannot take my delta equal to epsilon in this case. So delta should be less than epsilon in this case, because delta is my neighborhood of x. I'll be using it for the x. Yeah? So if epsilon is less than or equal to pi over 2, this gets better, and it's actually, this is what I have. Yeah? That's in the case when epsilon is less than pi over 2, I can just take my delta equal to epsilon, and this statement will exactly hold. So I can combine those two conditions. We can combine two conditions by choosing delta, delta is equal to the minimum of epsilon or pi over 2. So when I choose delta, minimum of those two, whichever is smaller, the proof is done. I can complete my proof, which means that for any epsilon more than 0, there exists delta is equal to minimum of epsilon or pi over 2. Yeah, it's positive delta minimum of epsilon pi over 2, which is obviously positive, such that as long as for any x, as long as my x is in the delta neighborhood of 0, this is what it means, the absolute value of x is less than delta, it exactly implies, what it implies, yeah, x is a neighborhood of delta neighborhood of 0, it means that this function is in the neighborhood of 1 is less than delta, which is equal to epsilon in this case. This is how I have chosen my delta, which is sine x over x minus 1 is less than epsilon. By choosing delta equal to the minimum of epsilon or pi over 2, whichever is smaller, in general it means, it actually means that delta is less than or equal to epsilon. Yeah, that's the condition for my delta. When I choose my delta this way, then for any epsilon, when x is the delta neighborhood of 0, it will exactly imply from here, it will exactly imply that sine x over x minus 1 will be less than epsilon, because delta is equal to epsilon in this case, which completes the proof. That's exactly the beginning, the embryo of mathematical analysis. This is how you prove that your function has a limit at the given point L, which is equal to 1 in our case. I hope that was clear, interesting, useful, and informative. This pi over 2 pops out because of the initial setup condition. X angle was in the first quadrant. And I also hope you enjoyed that. That was the mathematical analysis approach of the proof. The first wonderful limit. Please stay tuned for the wonderful limit number 2. Thank you very much. Have a nice day. Talk to you soon. Bye-bye.